based upon the interaction between the dp and the dm, dispersal phase and dispersion medium. We are further classifying the colloids into classification of colloids based on interaction between dp and dm. Based on interaction between the dp and the dm, we are classifying the colloidal solutions into two types: lyophilic salts. Why? Because colloidal solutions we call as salts simply. And the third one is lyophobic salts and lyophobic salts. Lyophilic, philic means loving, lyo means solvent. Simply lyophilic salts means they are solvent loving, whereas lyophobic, phobic means phobia, they hates. Okay, they are solvent hating salts. Okay, next one, these lyophilic salts are more stable. They are more stable. There was no need of any external stabilizing agents, whereas lyophobic are less stable. So we need some stabilizing agents for this. And lyophilic means there was more interactions, strong interactions between dp and dm. Was a more interaction, so they can uniformly mix and they form. Whereas lyophobic usually there was a less or very almost no interaction between dp and dm. That is why they forms immiscible liquids. And coming to the lyophilic salts, the stability of lyophilic salts, not only because of these charges, the stability of these lyophilic salts are no doubt they are stable. What is the reason behind the stability of lyophilic salts? The reason behind this is lyophilic salts are more stable because of their charge, because of the magnitude of the charge, and also one more reason, because of its hydration or solvation. Two forces, two factors behind the stability is, one is the charge and the second one is what? Hydration. But lyophobic salts are less stable. That less stability is because of only one factor, that is because only charge. There was no solvation. Solvation is nothing but if there was a salt particle, the solvent molecule will surround it and they will stabilize that. Okay, that is process we call it as what? Solvation. But in this case, there was no interaction between the salt particle and the solvent. If there was no interaction, how the solvent molecule will surround it? There was no solvation in this case. Only the stability is because only the charge only. So this is about the lyophilic salts and lyophobic salts. And examples for the lyophilic salts. What are the examples for the lyophilic salts? And one more thing, lyophilic salts are formed by high molecular weight organic substances. So they are formed by high molecular weight containing organic substances. Like that means starch solution, sucrose, glucose solution, starch, glucose, like this, gum sugar, gum arabic. So this is all about lyophilic. Coming to the lyophobic, if you take lyophobic, they are formed by low molecular weight inorganic substances. Low molecular weight inorganic substances that forms lyophobic salt, whereas high molecular weight organic substances will form what? Lyophilic salts. Okay, clear? So this is about one classification. Next classification based on classification of colloids based on nature or type of dp particles. Nature of the dispersed phase particles. So based upon the nature and the type of the dispersed phase particles, so there was so many types are there. The first one is, three types are there mainly. So the first one is multi-molecular colloids. Multi-molecular colloids. The second one is macromolecular colloids. Macromolecular colloid. The third one is associated colloid. Associated colloid. Three types of colloids based upon the nature and the type of the dispersed phase particle. Multi-molecular colloid, macromolecular colloid, and the third one is what? Associated colloid. Yes, what is this multi-molecular colloids? Okay, so as we know, in order to become a colloid, what is the range of size of the particle? When the size of the particles is between 1 to 1000 nanometers, 1 to 1000 nanometer, then only it becomes what? Colloid. Then only it becomes colloid. So in this multi-molecular colloids, what happened? There was so many of smaller molecules, but they are not in the range of colloidal size. What happened? They all together, they accumulate together and they form a bigger molecule. Now this is in the range of colloidal size. Understood? So like this, many molecules associated together or aggregate together and they form colloidal size particle. That is why we call it the multi-molecular colloids. Multi-molecular colloids. So what are the examples for these multi-molecular colloids? So best example is sulfur salt and gold salt. So this is two best examples for multi-molecular colloids. Next one, macromolecular colloids. So when we dissolve this substance in the solution, these particles are already macro size. They are already in the range of colloidal particles. So there was no need of any aggregation or association. Okay, so when we prepare the solutions, in these solutions, okay, the size of particles are in the range of colloidal size. So one single molecule is enough and the single molecule is already in the range of colloidal size. So then that is a macromolecular. And examples for this, all organic substance. Macro means bigger, like you take a starch solution, glucose solution, gum arabic. So these all are proteins, the solutions of proteins, enzymes. These all will use what? Macromolecular colloids. Next, coming to the associated colloids. Associated colloids. Here only there was a slight difference between multi-molecular and associated colloid. Don't be confused. What is associated colloids? In these associated colloids only we will discuss mainly micelles. Micelles we will discuss here. First of all, let you know the difference between multi-molecular colloids and associated colloids. Multi-molecular colloids means here the molecules are small in size and a group of molecules getting aggregate together and they giving colloidal range of particles. That is called multi-molecular. They always aggregate together and giving colloidal particle. But associated colloids means here also the molecules are small in size. Here also those molecules are associating together and they are giving the range of colloidal size. But the difference is this association can take place only after a minimum concentration. That means here one point at a low concentration. At a low concentration, they act as normal electrolytes only. At a low concentration, these solutions act as normal electrolytes only. But at high concentration, what happened? They associated together and they forms what? Associated colloid. Okay, that means these colloids are forming only at after certain concentration, and that minimum concentration required to form a colloid will be called as a critical micelle concentration. And at what temperature this micelle formation takes place, that is what we call as a Kraft temperature. craft temperature. So here they may ask you the two questions related to the missles. So we will discuss what is missile, we will discuss in the next part. Okay, anyhow, what are the conditions required to form a missile formation? So in order to form a missile, the temperature of this temperature should be greater than craft temperature. That's the first condition. The temperature should be greater than craft temperature. What is the craft temperature? The minimum temperature required to form missile formation is called craft temperature. And the second condition is the concentration also should be greater than CMC. What is the CMC? Critical missile concentration. Temperature is above craft temperature and the concentration is above critical missile concentration, then only missile formation takes place. Missile formation takes place. Missile is nothing but associated colli. Okay, if you see the missile formation, missiles are generally formed by the soap water, soap solution. Best example, soap solution. If you take the soap molecules, soap is nothing but sodium or potassium stearate. Sodium or potassium stearate, that is C17H35COONe. That is this is what polar head and this is a non-polar tail. So we can represent like this. So this is the carbons, total 17 carbons, and here COO minus. Okay, it is having a negative charge. So this I am representing this as this is a polar head and this is tail. This is a polar head and this is what? Non-polar tail. Non-polar tail. And this polar head is having a polarity, so they are hydrophilic in nature, water loving in nature because of this polarity. Non-polar tail is hydrophobic in nature, hydrophilic in nature and hydrophobic in nature. So now here, when you have taken soap solution at a low concentration, suppose this is a soap solution, and at the surface what happened, how they are present, so their polar heads are hydrophilic, no? So like this they are present at the surface. But when this concentration is above, so if you further increase the concentration above the critical missile formation, now what happened, they will aggregate like this. How? Polar heads, no? Non-polar tail, and non-polar tails are hydrophobic. So they will like this, they will aggregate together, and this is what we call it as missile. Like this, the missile formation takes place. In this missile formation, all hydrophilic heads are outward and hydrophobic tails are inward. Like this, the missile formation takes place. So this is what missile formation. And the action of soap, if you take, suppose you consider this is one cloth, and there was some dust particle, grease particle, let us consider. So this is what generally grease particles are means hydrophobic. So what happened, when you add the soap water to this, what happened, this soap molecules will go and attach. And which part will attach? Tail or head? Tail will attach. Why? Because tails are hydrophobic. This is also hydrophobic because of the same nature. So like this, all hydrophobic tails will connected to this grease particle. And when we wash out with water, what is the nature of heads? Hydrophilic. So when we wash out with water, along with water, heads will come, and along with that heads are following by tail. The tail is connected to the grease. Like this, we remove the dust particle from the cloths. So this is the action of soap in washing. Okay. Next, let us move to the next concept. That is what? Preparation methods. Methods of preparation. Methods of preparation of colloids. After preparation, purification. Let us we discuss methods of preparation of colloids. Mainly the colloids we prepare by two ways. So one is dispersion method. Next one, condensation method. You may get that out. Dispersion and condensation. I just give a small example. Dispersion means there was a big lumps of molecules like this. So you are breaking, we are dispersing this into smaller molecules. This is a colloidal range. So this process we call this breaking the bigger molecules into colloidal range, we call it as what? Dispersion. Condensation means you have very smaller molecules. And these smaller molecules are associated together and they give you colloidal range. So this is a condensation and this is dispersion. Simple logic. Dispersion means breaking the larger molecules into colloidal molecules is called dispersion. Condensation means combination of smaller molecules into and association of smaller molecules into colloidal range, we call it as condensation. Okay, so there are two methods, dispersion methods and condensation methods. And under the dispersion method, we will discuss two ways. Okay, so one is mechanical dispersion. Here itself we will discuss. What is a mechanical dispersion? So here, by using ball mill, spin mill. Okay, so as we know, to crush the rice. Okay, we are using ball mills as rice mill, spin mill. So in this rice mill or ball mill, usually there was so what happened? This upper will rotate in a clockwise and the lower will rotate in anti-clockwise. In the reverse direction, when the molecules are crushed between the two rolls. That is what we call as a ball mill or a spin mill. And in that, the large bulky molecules are converted into what? Colloidal molecule. That is what we call as a mechanical dispersion. Clear? Next, move to the second one. That is what? Peptization. Yes, what is a peptization? First of all, you should know what is a peptization. Peptization is nothing but this is a process of conversion of precipitates. So as we know in the starting of colloids, we discussed crystalloids, colloids, precipitates. Precipitates means they have larger size, more than 1000 nanometers. So process of conversion of precipitates into colloids by addition of smaller amounts of what? Electrolytes. See, one point here should be smaller amounts. We should not add electrolyte in bigger amounts. By adding very small amounts of electrolytes, we are converting the precipitates into what? Colloids. That process we call it as what? Peptization. Very important. So what is the problem? If we add the electrolyte in bigger amounts, what will happen? Let us we'll discuss it later. First of all, so this peptization process is based upon preferential adsorption of ions. Preferential adsorption. So peptization is based upon preferential adsorption. Okay, let us see. Preferential adsorption. So if you see that, if you take the preferential adsorption, you take ferric hydroxide. I am taking ferric hydroxide. To this ferric hydroxide, usually the ferric hydroxide, to this I am adding FeCl3. So the FeCl3, what happened? The molecules are, suppose this is a molecule, ferric hydroxide molecule. On the surface of the ferric hydroxide molecule, the Fe+3 ions are preferentially adsorbed. Because of the preferential adsorption of the positive ions, the common ion on its surface, what is the charge over this particle? What is the charge over it? Positive charge. Okay, so first suppose if you take the precipitate, how the precipitate will form? Suppose you consider this is the precipitate. So like this, all particles are gathered together and they form precipitate. Suppose if you separate these molecules from each other, then they forms what? Colloidal solution. How we are separating? See that. To disperse these molecules into the solution, what I am doing, I am adding an electrolyte in smaller amounts, which is a common ion to its molecules. So like for ferric hydroxide FeCl3, here Fe plus 2 plus 3 ion is what? Common ion. So when you adding, what happens, the Fe plus 3 ions will go and attach on its surfaces. What is the charge over it? Plus charge. But positive will repel together, so that the molecules are going further. So like this, what happens, we are separating. There is nothing but colloidal solution. You may get the doubt. What will happen if we add excess amount of electrolyte? If we add excess amount of electrolyte, first of all, what happens after this total surface area have been accommodated by the common ion? Okay, no problem. But if we add the excess amounts, what happens? That excess ions, the excess anions are there. That excess anions now they will attack on these positive ions. They will bring back their ions. So that there was no charge. If there was no charge, they again will combine together. Again the precipitation will take place. That is why you should make sure that during the peptidization, in order to convert the precipitate into colloidal solution, you should add very less amount of electrolyte only. If you add excess amount of electrolyte, what happens? That excess ions will come and bring back their cations or anions, bring back their ions. So there was no charge. If there was no charge, again they will accumulate together and there was a formation of precipitate again. So that is the actual problem. Okay, anyhow, so this is about peptidization. Understood? No? Peptidization is nothing but the process of conversion of a precipitate into a colloidal solution by adding a smaller amount of electrolyte is called what? Peptidization. Okay. Next, we move to the next Briggs arc method. Here itself we will discuss Briggs arc method. Actually, this is a special method. No? Why? Because in this Briggs arc method, both dispersion and condensation both will take place. That is why I am not including this Briggs arc method in any dispersion phase and a condensation phase. Under the dispersion, we discussed mechanical dispersion, peptidization, and under the condensation, there was a solvent exchange method, and one more thing is chemical method. Those two methods are coming under condensation methods. But this Briggs arc method, it is a special method where both dispersion and as well as condensation takes place. And one more thing, this Briggs arc method is specifically used for the preparation of colloidal solution of gold, silver and platinum. For these three metals they use for the preparation of gold salt, silver salt, platinum salt. Okay, they use this Briggs arc method. Let us see what is this Briggs arc method. In this Briggs arc method, they will take a large container, and in that container there was a smaller container, and between the smaller container and large container there was an ice cubes. So this is the ice cube. Okay, and these are the two. Suppose I am taking gold, two rods. Okay, and they forms. First of all, when you connect this to external source, what happens? They produces arc, electrical arc, and after some time, what happens? Because of this electrical arc, these rods will generate what they generate? Vapors they generate. Understood? Because of this high electrical arc, the metals that we are using, either if you use gold rods or silver rods or platinum rods, whatever it may be, when you use whatever the rods are using, those rods will evaporate and undergo what? Vaporization, a dispersion. There is nothing but dispersion. Okay, so after that what happened? Because of this low temperature, again they will condense back, and they'll come out as what? AU. Now after they condense back, what happens? They will react with the OH minus ions and they forms, and onto the surface. Onto the surface, OH minus ions will go and they forms negative salts. Okay, like this we can produce salts, that is a silver, gold and a platinum salts by this Briggs arc method. Remember that. So in this Briggs arc method we can prepare the salt of gold, silver and platinum. So this is a Bredig solving method. Next let us go to the condensation method. In this condensation method, I'm not going in detail about the condensation methods. Chemical methods are there: double displacement method and oxidation method, reduction method and hydrolysis method. 4 methods are there. You just go to the NCERT. They are not much important. Next, solvent exchange method. By changing the solvent, okay, there was a formation of colloids. Okay, that is what we call it as a solvent exchange method. So this is about the methods of preparation. And after we prepare the colloidal solutions, we cannot prepare the 100% pure colloidal solution. We should be purified before we are going to use them. So that is what we call it as a methods of purification of colloids. What are the purification methods? Purification methods. So we follow the following methods for the purification. So one is dialysis method. The second one is electrodialysis, and the third one is ultrafiltration. Dialysis, electrodialysis and ultrafiltration. Is what is the dialysis, electrodialysis and ultrafiltration? Dialysis is nothing but here they use a membrane, selective permeable membrane as a bag. In that bag, within the bag they take solution, whatever the solution they want to purify, and they will keep it in a external solvent. Okay, what happens? That selective permeable membrane will allow only in one direction. So whatever the all soluble impurities that were present within the bag, they will come out. Okay, all soluble impurities will come out. That is what we call as dialysis. Okay, best example, the patients who suffered with a kidney failure. Okay, so they will do the dialysis, the filtration of the blood based upon dialysis only. But remember that dialysis process is very slow process. So to speed up the dialysis process, we follow electrodialysis by using the electrodes. Okay, by supplying the electrical potential. If we speed up the dialysis process, that is what we call as electrodialysis. The principle behind this is the same, but here we will use only electrical potential. Next, ultrafiltration. If we filter the colloidal solution by using ultrafilters, what is the difference between filter and ultrafiltration? Filtration means if you do the filtration by using only normal filter paper, that is a filtration. Ultrafilter papers. How to prepare the ultrafilter paper? You may get that out. Yes. What is the difference? Filter paper having somewhat bigger size pore. The pore size is bigger compared to the ultrafilter papers. So, how to prepare the ultrafilter paper? How to reduce the size of the pore? Yes, simply by dip the filter paper in collodion solution. By dipping the filter paper in collodion, we can reduce the size of the pore. That is what we call ultrafilter paper. You may get what is a collodion. Colloidal solution is collodion is nothing but 4% cellulose nitrate in alcohol and ether solvent. Okay, 4% cellulose nitrate in alcohol and ether. That is what we call as a collodion. By dipping the filter paper, normal paper, filter papers in a collodion, we can reduce the size of the pore. That is what we call ultrafilter. By using this ultrafilter paper, if we separate the soluble salts, soluble impurities from the colloidal solution, that is called ultrafiltration. So these are the methods of purification. Next, properties.